Okay, welcome back everyone. We're on notes number 17, and today we're going to talk about derivatives in general. So in our last couple of lessons, we learned about the derivative, which is the slope of the tangent line to a curve at a point. And we've been finding the derivative at a particular point, like x equals 1, x equals 2, something like that. Today we're going to generalize it, and this is going to lead us along a path of many weeks of learning how to find general derivatives of all kinds of things. We won't continue to do it with limits forever because we will learn some shortcuts. First of all, I want to go over the big idea, which is that if you want the instantaneous rate of change, then what you're looking to find is the slope of the curve at a point. Now, how do you get the slope of a curve? Well, it's really the slope of the tangent line to the curve at the point. And what is the slope of the tangent line at a point? As I said earlier, that's what we know as the derivative. So keep in mind that when you're finding a derivative, and as we go through this course for the rest of the year, every time we're finding a derivative, what we're really doing is finding an instantaneous rate of change. Okay. The mathematical definition of derivative. You've seen it a couple of times this week with the different definitions we've been working through. The derivative of f of x at the specific point x equals a is given a specific kind of notation. It's called f prime of a, and it looks like this. You put a little tick mark or a prime sign between the f and the a, so what we say is f prime of a. And we've already learned that f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. So the quotient itself is the slope of the secant line, but when you take the limit of that slope as x approaches a and those 2 points get infinitely close together, that gives you the slope of the tangent line. We also learned a different definition for it. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. And as I said earlier, we've been using it to find something like f prime of 1, f prime of 2, f prime of 3. So we're using a specific number for our x value. We're calling it a, but we're using a specific number for a. Now, suppose you don't want to find the derivative at a specific point, but you just want to find an expression for the derivative in general. The general derivative of f of x is called f prime of x. We just replace the a with an x. So we can take the previous definition, the limit as h goes to 0, and we can just replace the a with the x, and we get the limit as h approaches 0 of f of x plus h minus f of x over h as the definition of f prime of x. Now, what if we wanted to go back to our first definition of f prime of a and change the a to an x? What would that look like? If we replace the a with an x, we get f prime of x equals the limit as x approaches x of f of x minus f of x over x minus x, and this is not really working. This notation isn't making any sense, so we're not able to translate that version of the definition into just x's, but we'll still be able to use it whenever we want to, and I'll show you how. Now, talking about notation, let's do a little bit of mathematical history here for a moment. So there were two individuals who were developing calculus really pretty much at the same time, but independently of one another in different locations. We have Newton, yes, that's Sir Isaac Newton, and we have Leibniz, Gottfried Leibniz. Well, because they were working independently of one another, they each had their own kind of notation. So Newton is credited with using the function notation, like f of x, and so Newton is credited with the derivative notation f prime of x. Now Leibniz was doing his own thing, and so he's credited with this other notation. So suppose instead of calling a function f of x, we just call it y, and then the way we describe the derivative symbolically is dy dx. Now this has some meaning because dy is kind of like delta y, where delta means change. So dy may just be an infinitesimal change. And similarly, dx is kind of like delta x. Again, delta means change. So basically what we have is the change in y over the change in x. Just like slope, change in y over change in x. So that's why that kind of notation makes sense. So we'll use both types of notation, and I want you to be familiar with both of them. So let's say we have this problem. Find the derivative of y equals 2x at the point x equals 4. Okay, so what would Newton do? Well, Newton would probably call it f of x equals 2x as opposed to y equals 2x, and then we can describe the derivative as f prime of 4. What would Leibniz do? Well, Leibniz doesn't have to change the name of the function. We can still call it y equals 2x. But in order to show that we're finding the derivative at a particular point, we have our symbol for derivative, dy dx, followed by this vertical bar, which means such that, and then we just say what the x value is going to be. So dy dx such that, or evaluated at, x equals 4. So that's just saying find the derivative at 4. Okay, let's do some examples. Number 1, if f of x equals 1 minus x cubed, find f prime of x. And then there's other things we're going to do. But let's focus on the first part, find f prime of x. Let's do it both ways. So one way would be using the limit. I'm going to squeeze in a little more room here. Using the limit as x approaches a of f of x minus f of a over x minus a. This is going to give me f prime of a, and then when I get to the very end, I'll just replace the a with an x to call it f prime of x. So we have the limit as x approaches a of our function 1 minus x cubed minus our function with a plugged in. That's going to be 1 minus a cubed. Be sure to put parentheses around it, over x minus a. Now let's simplify. So we have the limit as x approaches a of 1 minus x cubed minus 1 plus a cubed over x minus a. Notice that we can cancel the 1 and the negative 1. And so we have the limit as x approaches a of the opposite of x cubed plus a cubed. I'm going to write that as a cubed minus x cubed over x minus a. Now, I'm sure you all remember from pre-calculus what to do if you have a difference of cubes, right? If you have a difference of cubes, there's a factoring formula for that. Remember the SOAP formula? Same, opposite, always positive. So if you have a cubed minus b cubed, it factors into a minus b times a squared plus ab plus b squared. So if I factor that numerator, we get a minus x times a squared plus ax plus x squared, and then on the bottom we have x minus a. What are we going to do with a minus x and x minus a? Remember, if you have opposites, they cancel to leave a negative 1 instead of a positive 1. just like 4 minus 2 and 2 minus 4, they would cancel to leave a -1. So I'm going to leave a -1 there. So here's what we have now. And finally, what I want to do to evaluate the limit is substitute a in for x. So we have f prime of a is equal to the opposite of a squared plus a times a is another a squared plus a squared again, -3a squared. But remember, we were asked to find f prime of x. So let's just remove the a and put an x in its place. F prime of x is -3x squared. That represents the derivative in general. Do you want to find the slope at x equals 1? Put a 1 in there. Do you want to find the slope at x equals 2? Put a 2 in there. Do you want to find the slope at x equals -99? Put a -99 in there. Now what I want to do is show you how we would do it using the other definition of derivative, and we'll get the same answer. So f prime of x is the limit as h approaches 0 of the function with x plus h plugged in would be 1 minus the quantity x plus h cubed minus the function with x plugged in is just 1 minus x squared, 1 minus x cubed over h. So I'm using this right here, and I'm putting the function in there. Okay, so we've got some simplifying to do. Quite a bit of simplifying in the numerator. Remember that x plus h cubed means x plus h times x plus h times x plus h. You don't just distribute the 3. And then here I'm going to distribute the minus sign, so -1 plus x cubed all over h. Okay, so we're going to multiply this whole thing out, the x plus h times x plus h, and then what we get with that we multiply by x plus h. There is a shortcut for that. It's using Pascal's triangle, but if you never learned it or you don't remember it, then you're just probably going to go through the motions of multiplying all that out. And what you should get when you multiply those 3 together would be x cubed plus 3x squared h plus 3x h squared plus h cubed. Now I'm ready to distribute the minus sign. Remember to keep your limit notation throughout the problem. So we have 1 minus x cubed minus 3x squared h minus 3x h squared minus h cubed minus 1 plus x cubed all over h. Okay, what cancels? Well, we have 1 minus 1, and we have minus x cubed plus x cubed. Now, after you've had some experience with this, and I know you've been evaluating some limits or doing some other derivatives with this technique, what you should have left after canceling is just terms that are multiples of h, so that you can then factor h out of the numerator. If it doesn't work out that way, that tells you something went wrong. So let's factor h out of the numerator, leaving us with -3x squared minus 3xh minus h squared. And that way we can cancel the h from the top and the bottom. And now we're ready to put 0 in for h. So we have -3x squared minus 3x times 0 minus 0 squared. So we have -3x squared. That's the value of f prime of x. See, we got the same answer, doing it 2 different ways. Now, for this problem, you probably noticed that doing it the second way, it was more complicated in the numerator than the first way. It's just going to vary from problem to problem. Sometimes doing it the first way is more complicated because you have to figure out how to factor, like we had to use the factoring method, the difference of cubes. You have to figure out how to factor so that you can reduce. In the second method, there isn't going to be the factoring other than factoring out the h. It's just a matter of multiplying everything out and combining like terms. So pros and cons of both methods. Now, back to the problem. Find f prime of x, we did that, and use it to find an equation of the tangent line to the curve at the point 0, 1. So that's telling us that we're going to need to find the derivative at x equals 0. Okay, we can do that. Using the point 0, 1, f prime of 0 is going to be negative 3 times 0 squared. Well, that's just 0. So that's our slope. Remember, the derivative is the slope of the tangent line. So m equals 0, and we have the point 0, 1. So we can finish the process of finding the equation of the tangent line. Put in 1 for y, put in 0 for m, put in 0 for x, solve for b, you get b equals 1. Y equals 0, x plus 1 is just the line y equals 1. That's the tangent line to that point on that curve. And that curve was a cubic function, 1 minus x cubed. So it was a cubic function. Here's your standard y equals x cubed, but the negative would flip it upside down, and then the 1 would shift it up. So that means our function was something like this. That's just my rough sketch. Y equals 1 is this line. Well, that tells me that my curve is actually a little more flat right there because it just temporarily flattened out in order to have a horizontal tangent line. Okay, we do have several more examples. I think what I will do is make this a 2-video lesson. So we're going to end here with video 1, and then I'll pick it up with example 2 for video number 2. Thank you.